Now starting the next session. We'd like to begin by announcing paper awards. So we were very excited to have a number of extremely strong submissions to the workshop. Amongst these, we selected a small handful of awards. The recipients are Tom Wainforth for Tighter Elbows Are Not Necessarily Better, Jintar Carolina Zuigate for Entropy SGLD Optimizes the Prior of a Valid Pack-Based Bound, Alexander Amini for Spatial Uncertainty Sampling for End-to-End Control, Matthias Bauer and Matteo Roja Carula for Discriminative K-shot Learning Using Probabilistic Models, Jiri Hran for Two Problems with Variational Gaussian Dropout, John Lambert and Ozan Sener for Deep Learning Under Privileged Information, Dustin Tran for Generative Models for Alignment and Data Efficiency in Language, and Leonard Hasenclever and Rhiann Vanderberg for Variational Inference with Orthogonal Normalizing Flow. We would also very much like to thank our sponsors for making these awards possible: Google, Microsoft, Qualcomm, and Uber AI Labs. So let's have a round of applause for the sponsors and the award recipients. It is now a great pleasure to introduce Matt Hoffman, a senior research scientist at Google, who's going to be talking about stochastic gradient descent as approximate Bayesian inference.
Okay, thanks for the introduction and the invitation to be here. It's a privilege to be sharing this with you today. I'm going to be talking about our work on trying to interpret stochastic gradient descent as approximate Bayesian inference. This is a topic that has been getting, there's sort of been loose talk about for years, and more recently there's been a lot of really interesting work trying to make it more formal. So let's get started. So I'm going to assume that we have some data x and a Bayesian model with parameters theta. I'm really just sort of fixing notation here. We're interested in a posterior p of theta given x, and I'm going to start by thinking about maximum a posteriori estimation, where we're just trying to maximize the log joint probability of x and theta. Right, so just sort of classical optimization problem. As we all know, presumably, if we have a very large amount of data, then batch optimization is expensive, and this motivates stochastic gradient methods, which probably everybody in here is familiar with, where you just sample a data point at random, or a mini batch of data points at random, and then take a step in the direction of that, of a random unbiased estimate of the batch gradient, and decrease the learning rate, and keep going. And if you and this method has sort of surprisingly strong guarantees if you play around with if you use a classical decaying step size schedule, which in practice these days people don't. So just for intuition, right, here's an example where we're just trying to optimize a two-dimensional function. And you do SGD with a decreasing learning rate, and sure enough, it converges to a small region, sort of arbitrarily small region around the true optimum. If you instead use a large constant learning rate, then it converges quickly to a region around the optimum, but bounces around there and doesn't really ever converge to any small region around it. If you use a smaller learning rate, as you might expect, it converges to a smaller region around the optimum. So in this talk, I'm going to be focusing on the stationary distribution of what I'll call the constant SGD process. And that's a distribution, and this is the Bayesian Deep Learning Workshop. So the obvious question is, how does that distribution relate to the distribution that we all think we care about, which is the posterior p of theta given x? And in particular, what can we do to control that distribution using the small number of tools that we have, which are step sizes and preconditioners? So again, just to fix some notation, I'll be calling these G hats our stochastic gradients. I'll use this C matrix, which is the covariance of the noise in those gradients, is going to be pretty important. I'll use A to denote the Hessian of the objective at some point theta. I'm going to assume we're doing mini-batch stochastic gradients, or we're going to have mini-batches of size S. And without loss of generality, let's assume that the minimum we're interested in is at 0, just to keep the notation simple. So, of course, we're not going to be able to get anywhere unless we make some assumptions. So, and these assumptions, I'm not going to pretend that these assumptions aren't strong, but they're not totally ridiculous either. So I'm going to spend some time on this slide, and if you want to totally dismiss this work and say that it's totally irrelevant to the things you care about, which it might be, this is the slide to pay attention to. So big assumption number one, we're going to say that our gradient noise is approximately Gaussian. And full rank, actually. So there's a lot of situations where that's not true, but there are situations where it is true, right? If your mini-batch is large enough and your parameter space is not too enormous, then you can probably appeal, and your gradients aren't too sparse, and you can probably appeal to the central limit theorem. Next assumption, I'm going to assume that the covariance doesn't depend on the current values of the parameters theta. Excuse me. If we're sort of constrained to a small enough region around the optimum and our third derivatives basically aren't too big, this is going to be approximately true. We're going to approximate the discrete time stochastic gradient descent process with a continuous time limit, which is reasonable for small enough step sizes. This is something that could probably be relaxed, but it makes the analysis easier. And finally, I'm going to assume that the posterior is Gaussian, and that the log posterior can therefore be approximated by a quadratic. And this is valid in the usual kind of Bayesian central limit theorem setting, where you've got large n and a small number, relatively small number of parameters relative to n, and your probabilities are smooth. Right. So these are the core assumptions that we're going to be making for the rest of the talk. If you disagree with them, then some of our conclusions will change. And so, I want to be upfront about that, but I think, probably these assumptions could be relaxed in some cases also. There's been some recent work looking at that, which is really interesting. We were sort of trying to make our lives as easy as possible in some sense by making these assumptions. So if you make those assumptions, then what you wind up with is that constant SGD is simulating an Ornstein-Uhlenbeck process, which is this classical drift diffusion process in continuous time, right? So basically what's happening is the change in theta is basically you multiply theta by this Hessian, and then there's this sort of preconditioned Wiener process that's a diffusion term. This is a pretty well understood and well studied process. Its stationary distribution is Gaussian. It has a covariance sigma. It's not in general easy to say exactly what sigma looks like, but it does satisfy this property on the right, that A sigma plus sigma A is equal to epsilon over S times the so the Hessian times the constant SGD covariance plus that covariance times the Hessian is the step size divided by the mini-batch size times the gradient noise covariance. That might look like a kind of random thing to observe, but it turns out to be useful for interpreting SGD as a variational approximation. So just to validate our assumption, show you that they are true-ish in some situation. This is a Bayesian logistic regression problem. Black line is an equal probability contour of the true posterior. The yellow line is what the theory predicts the iterates covariance should look like. The red line is sorry, the yellow line is what constant SGD iterates actually look like. Red line is what the theory predicts. It's pretty close. So I am saying that constant SGD has the stationary distribution Q, which approximately follows an Ornstein-Uhlenbeck process. let's say we have only one parameter, which is step size. Can we tune that step size to make Q as close as possible to the posterior? This is, a knee-jerk reaction is maybe we can minimize KL from Q to P, and in fact, it turns out that that winds up being pretty tractable. I won't go through all the steps here, but you'll notice that there is that sigma A plus A sigma term, which we're observing is equal to epsilon over 2 times the trace of C, plus some constants. And so optimizing this to minimizing this over epsilon is pretty easy. And you wind up with this sort of halfway intuitive, somewhat classical result that the step size epsilon that you should use is 2 times mini batch size divided by data set size divided by the average variance of your gradients, right? So this is saying, in some sense, the noisier your gradients are, the smaller your step size needs to be. That's intuitive. The larger your mini batch size is, the larger your step size can be because you've, again, reduced noise. And the larger your data set is, the smaller your step size should be because your posterior is going to be more concentrated. So it all sort of makes sense. We can look at what happens if you actually implement this on a couple of examples. So here the blue X's are samples from the posterior. The cyan crosses are samples from this constant SGD process. And if you choose this optimal epsilon, then you wind up with something that looks a lot like kind of the sort of underdispersed variational distributions that we that we tend to see when we use other kind of variational approximations. We can take this a little further and ask what happens if instead of a scalar step size epsilon, we use some preconditioner H. Then it turns out that the optimal thing to do is to make that preconditioner proportional to the inverse of the gradient covariance, which is sort of intuitive, and also is also consistent with the recommendations in these excellent stochastic gradient Fisher scoring paper from a few years ago. If you want to make a diagonal approximation like they suggest in that paper, then our theory suggests that you should do exactly what they did in that paper, where it was sort of just proposed as a heuristic. So that's nice to get confirmation on. It's interesting to compare how these results look for different, how the results of different methods actually look, right, and sort of what you get if you use this full covariance approximation, or if you do a more conventional black box variational inference approach where you explicitly have some Gaussian whose parameters you're optimizing. So of course, if you give yourself more parameters to tune the stationary distribution, it looks more like the posterior, and it can look actually pretty okay, as the theory suggests it should. And actually, if you only use this scalar step size, you end up with results that look really not much different or worse than what happens if you do black box variational inference with an explicit Gaussian approximation, which is interesting that this kind of really kind of just dumb, like, take stochastic gradients with and don't change the step size, but try not to use the step size that's the wrong size, gets you to the same place as this somewhat more sophisticated variational approximation does. There are a couple extensions we look at as well. Iterative averaging is a really interesting one. So this is if you don't know about it, this is a really cool algorithm that has almost sort of astonishing properties. So it's this very simple idea that you run SGD and you keep a running average of the iterates of your SGD process. And Polyak and Yuditsky showed that asymptotically, if you're sort of careful about learning rates, it's literally impossible to do better than this in sort of a first-order Oracle framework. That actually, any fancy preconditioning you might want to do, any other fancy stuff you might want to do, there's no point if you could just do iterative averaging. it's a remarkably powerful algorithm considering how dead simple it is. So if you buy our assumptions A1 through A4, then you can ask what is the covariance of these averaged iterates after some number of iterations t. And it turns out to be this thing, which is proportional to 1 over t. That sort of makes sense because you're averaging over t things. 1 over the mini batch size, that makes sense too. A inverse times gradient covariance times A inverse, that is the sort of thing you tend to see in the iterative averaging literature. And then this second order term. The interesting thing about that first term is that it's independent of step size and preconditioners. So this is the sense in which iterative averaging is optimal, right? That no matter what preconditioning you did, assuming you can ignore that second order term, basically everything is, the result is exactly the same, which is pretty interesting, I think. And not, not novel to us necessarily. That's been known for a long time. If we make one more assumption that the data actually came from some p of x given theta in our model class, and we've got a large enough n that we can sort of invoke the Bernstein-von Mises theorem in the usual way, then it turns out, perhaps surprisingly, but this is sort of just a classic identity about the Fisher information matrix, that the Hessian A is equal to the gradient covariance C. If you plug that into the stationary distribution, then the A inverse and the C cancel, and we have 1 over t times S times A inverse. Doing a little bit of multiplying by 1, we wind up with this result that we have n over t times S times the covariance of the posterior that we assumed was Gaussian, right? That covariance is going to be proportional to 1 over the size of the data set times the, and then the shape will be given by the inverse Hessian. So that sort of obviously suggests that we should set t equal to we should set t equal to n over s, right? The size of our data set divided by our mini batch size, which is to say that we should be averaging over exactly 1 epoch to get a sample from the posterior. You might be wondering about those second order terms that I've been ignoring. Obviously, they can matter in practice, so I'll just say an aside about those. I won't go into too much detail about this derivation with all these sort of weird eigendecompositions and stuff, but basically the story is that if the step size divided by the mini batch size is large enough and the number of iterations is large enough, then you don't really need to worry all that much about these second order terms. So that's sort of in tension with the justification that I gave for the assumptions we made earlier, that are only justified for relatively small epsilons. You sort of want to be in this sweet spot. And when can you be in that sweet spot of sort of step sizes that are small enough that the theory is reasonable, but large enough that you actually are mixing at some kind of reasonable rate and averaging does something useful? Basically, the answer is if n is large so that t can be large and the condition number isn't too bad, then you can get away with this. So again, just validating assumptions on a synthetic linear regression example where we know that the assumptions we made are kind of reasonable. In fact, the posterior covariance does look a lot like the covariance of the average iterates, and also as predicted by the theory, the covariance of the constant SGD process is isotropic. So I think this is a pretty interesting result that you can sort of turn this classical optimization algorithm that's really simple to implement into, in some sense, an optimal MCMC algorithm. It's also sort of a negative result in some sense in that it's pretty, once you sort of see that, it's sort of obvious that under our assumptions, all of which I would say are optimistic, it's possible to generate a posterior sample in order n time, but insofar as iterative averaging is the best possible first order Oracle stochastic gradient algorithm, if you could generate a posterior sample faster than order n time, then you could basically come up with a better optimization algorithm than iterative averaging, which we know isn't possible. And so basically you know, it's sort of intuitive, right, that you sort of have to look at the whole data set if you really want a posterior sample, but this is sort of a way of seeing that in a rigorous way. So to summarize, we're presenting a way to tune constant stochastic gradient descent, which we usually think of as an optimization algorithm, to do what is essentially Markov chain Monte Carlo sampling on a variational approximation to a posterior distribution. So that sentence contains basically all of my favorite words, and so that makes me happy. I'd say this is also a nice framework for analyzing stochastic gradient MCMC algorithms. And finally, iterative averaging is you know, we all knew that iterative averaging is great, but maybe it's even better than we realized. Couple just discussion points. This analysis sort of, sometimes in deep learning people talk about the sort of sharp versus flat minima thing. I would say that this analysis is sort of relevant to that probably. You know, Sam Smith was talking about that earlier also during the poster session. And of course, this is the Bayesian deep learning workshop, so there is this question of whether any of this stuff actually applies to neural networks. I'd say the answer is not obvious, right? So we did assume that the gradient noise was full rank if you have an over-parameterized model with a huge number of parameters relative to your data set, then your gradient noise is not going to be full rank, let alone Gaussian. And so that's a concern. I would like to sort of understand that a little better. Also, you know, in the neural network world, I think, you know, what prior assumptions you make matters enormously, and probably some of the quadratic approximations that we're making are not totally realistic in that scenario. It seems like there's been a little bit of very recent work that's trying to relax some of these assumptions, which is very exciting. And I would love to see more of it. So, you know, if anybody wants to do that work and tell me about it, then please do. So that's it. If there's any time for questions, I'll take them. Thanks.
Okay, we have time for some questions. Please come closer to the microphones.
Hi, thanks for an excellent talk. Fantastic. So do you know about work, I think Yi-Wai Tay and his postdoc, I forgot his name, Vollmer maybe? They did a very extensive analysis, I think, of the convergence rates of these kind of, you know about that work?
The convergence rates of like SGLD?
Yeah.
Yeah, I mean, I won't claim to have read it in detail and understood all of it, but I got the headlines.
Is that kind of related?
Yeah, I think it's, so one way of reading our analysis of SGLD is that it, if you buy all of our assumptions, which, you know, in some cases you can and in some cases you shouldn't, then basically it's related also to the stochastic gradient Fisher scoring story, right? That there's all this noise coming from your stochastic gradients, sort of classical SGLD, I can call it that because it's 6 years old. That's, you know, antiquity now. So classical SGLD basically says you have to average away all of that noise and replace it with this artificial noise. And of course, you know, averaging away large amounts of noise is an expensive thing to do. You know, I really like the stochastic gradient Fisher scoring paper because it observes that, you know, we have this noise and you can do, you know, you can use it instead of trying to average it away. And I would, you know, you have to make some assumptions for that to be a really totally valid thing to do, but I would think that the rates there would be a lot better.
Great, thanks.
There are more questions? Okay, let's thank the speaker.
Thanks again.